So again, the continuing with where we left off on the last video, if you wanted to make a perfect buffer solution, which, as again we were saying, is one that contains a 50-50 mixture of the conjugate base and acid form of a weak acid, there's an easier way to do it as compared to calculating that exact amount of base to add. All right, and it comes from taking advantage of what we know about the relationship between the relative amounts of the conjugate base and weak acid, the pKa of a weak acid, and the pH. All right. So again, this is the Henderson-Hasselbalch equation. So pH would just be the pH of whatever the solution is. All right. That's what you can measure with a pH meter. All right. The pKa is the pKa of the weak acid. All right. So for example, if we're using methanoic acid, for example, its pKa is something that we could look up in the data table. All right, and again, going back to that unit, pKa is essentially it's a measure of how tightly it holds on to that acidic proton. All right, if it holds on to the hydrogen really tight, it's going to have a relatively high pKa. But if it releases that H plus relatively easily, it's going to have a low pKa, right? So that would be whatever that number is right there. And this is just a ratio of how much of the two forms you could have. All right, so you're either going to have it in its acid form or in its conjugate base form. And essentially what happens is that the pH is going to have an effect on that ratio. All right, the pKa stays constant. So in our buffer solution, remember that we want to have a 50-50 mixture of the conjugate base and acid. All right, so if you have a 50-50 mixture of these guys, all right, the ratio of A minus to HA would be 1. All right, so if you put 50 in the numerator and 50 in the denominator, anytime these guys are equal to each other, that ratio equals 1. So we could plug that into this equation right here. We would say the log of 1. All right, and the log of 1 is 0. All right, so what this says is that if you have a 50, in order to have a 50-50 ratio between these two guys, these two chemical species, that's going to happen when the pH is equal to the pKa. All right, so in order to get that 50-50 ratio, you just take your solution and you adjust the pH to make it so that it's the pKa of the weak acid. So if you want a little pictorial of how that would work, let's just say that we started this little representation that just shows a pH meter. All right, so we're just going to put a pH probe into the mixture. Let's say we start off just with pure water. We would expect that its pH would be 7. All right, let's then add some methanoic acid. All right, and let's pretend that we add 1 mole of that to 1 liter of water. All right, well, when you do that, we calculated earlier that the pH would be 1.88. That's what our pH meter is reading. All right, so in order to make the buffer, all right, so at this point you would not say that it's a buffer solution, all right, because it doesn't have that 50-50 mixture. We're going to add some sodium hydroxide, and what's that's going to do is it's going to convert some of this to the conjugate base. All right, remember, we don't want to convert all of it because we want that half-half mixture. All right, so what we're going to do is we're just going to pay attention to this pH meter as we're dropping in sodium hydroxide solution. So instead of calculating that exact amount of sodium hydroxide that we would need, let's just monitor the pH. And once the pH gets to be the same as the pKa, all right, remember the pKa is something that we could look up in the data table. When that pH equals that pKa value, we know that the ratio of the two forms, of these two forms, would be 50-50. All right, and so that's the way that we're going to get to that ideal buffer. All right. All right. So in this next part, we're going to talk about what buffers have to do with the pH curve that we talked about earlier. All right. So and I know I put this sideways in here. It's because I want to be able to draw on this page in this orientation right here. But we said earlier that pH curves illustrated the concept of buffers. All right. So, but why is that? What is this pH curve that we talked about earlier in the unit, what does that have anything to do with buffers? All right. So, first of all, to give you a little orientation, I know that there's a lot. There's going to be a lot on this page right here, and that's why I devoted an entire page to it. All right. What we're going to be what I'm showing you here is the titration of a weak acid with a strong base. All right. So remember. So this would be pH on this axis right here. Let's zoom out a little bit. All right, and so that's pH on this axis. This is volume of your. This is volume of the base that you would have added. All right. So remember, since it's a weak acid, we would expect the starting point to be a little bit less than 7. Or rather, what I should say is that its pH should be somewhat should be less than 7. It could be 4, could be 2, but it's definitely not going to be way down here around 0 to 1, because that's where you would expect a strong acid to start off with. All right, so let's just, it's going to be, let's say, for example, a pH of about 5. All right, and we saw that it's relatively slow growth right here, but then it takes this sharp rise, all right, and then levels out again. All right, and we talked about a couple aspects of this earlier in the unit. All right, for example, we said that in this region right here, when you hit that inflection point, and that inflection point is going to be halfway between this part right here and this part right here, we call that the equivalence point. And that's going to be when the number of moles of base that we've added, all right, remember we're adding base down here, equals the number of moles of weak acid that we started with. So however many moles of weak acid we started with to make the solution, that's going to be the point where we've got a 1, for every 1 mole of the acid, we now will have added 1 mole of the base. So if you want a little cartoon of that, remember we're starting off with our weak acid solution. We're dripping sodium hydroxide solution into that, and the reaction that's going to be going on is this. All right, so we've got a solution of HA, of weak acid, and we're adding NaOH. All right, and this would be the overall reaction that's occurring as we're adding the sodium hydroxide. All right, and at this point right here, the equivalence point, that would be the point where for every 1 of these, we've added 1 of these. All right, up until that point, we've got way more of this in this solution than we've added sodium hydroxide. All right, so let's talk about what we're going to have in the solution at different points in this curve. All right, so at the equivalence point, essentially it's going to be all. I put all A minus in quotation marks, and I just want to point out that's not actually true, because at that point, all right, we're going to have some amount of, and I left a little bit out. We're going to have some amount of HA, because A minus can act as a weak base to give a little bit of the A minus. All right, we can compare that to. All right, we can compare that to what you would have at the start. At the start, you would have, quote, all HA, and that's not really, because you have some amount of this reaction going on. All right, so let's pretend that you added HA to water. All right, this can act as a weak acid with water, creating a small amount of A minus. All right, so the reaction that you can write in here is that A minus could react with H2O to give OH minus plus HA. All right, so that's why it's not exactly true, but we're going to simplify this a little bit and just say that at the start you essentially have all HA. All right, at the equivalence point you're going to have all A minus, and we can make some assumptions about what's going on in between. All right, so in the very start of the reaction, all right, you would expect in this arrow, this arrow is going to be pointing down to about this. Let's say it's pointing to this point on the curve. All right, so at this point on the curve, we've added a little bit of sodium hydroxide. All right, so you're still going to have mostly HA. All right, we've got a solution of this, and we've just added a couple drops of this. You're still going to have mostly this stuff right here. All right, But as we continue to go on, well, almost right before we get to the equivalence point where we said that it's all A minus, we could assume that we're going to have mostly A minus, and that's going to be like maybe about this point in the curve right here. All right, so we know that right here you've got mostly HA and this is mostly A minus. There's going to be some point in between where you got this 50-50 mixture of HA and A minus. All right, so how do we find that point where it's going to be 50-50? Well, here's the logic that we're going to use. All right, we know this equivalence point is where for every 1 mole of base you've added, that would be equivalent to 1 mole of weak acid that you originally had. Oops. All right, so if by this graph we could figure out that we needed to add 10 milliliters of the base, that's the amount of sodium hydroxide for 1 mole of NaOH to have been added per 1 mole of HA. So if that's the amount that's necessary to have a 1-to-1 mole ratio between the sodium hydroxide and the A minus, well, in order to get half of that, to get half of this reaction to go, right? So this is the amount required for a 1-to-1 ratio. Then we would need to add half of that amount in order for there to be a 0.5-to-1 ratio of this reaction to occur. So then if this is the amount required for 1-to-1, then half that volume is what's necessary for a 0.5 mole of NaOH per 1 mole of your weak acid. And it's at that point is called the halfway point. All right, so that's when we're halfway to fully completing this reaction right here. All right, so that halfway point is going to be important. All right, because that halfway point is going to be the point where in your buffer, in your solution, in that bottom solution that you've been adding your base to, you will now have a 50-50 ratio of acid to conjugate base. All right, so the reason that's important is it allows us to figure out, to calculate what the pKa of the weak acid is. All right, so let's say you handed somebody an unknown weak acid and you said, all right, we need you to calculate the pKa of this weak acid. Well, here's something that let's go back to this right here. Well, we know that at the point where these guys are equal to each other, all right, whatever the pH is, that's the pKa of that weak acid. So if this was an unknown weak acid, and we looked at this graph, we could say, well, that's the equivalence point. Well, that's the halfway point, which represents when you got a 50-50 ratio of those guys. Well, let's go up to that point right there, and let's take that point and go over to the graph right here, and whatever that pH is, when that line goes over, that would be the pKa of that weak acid. All right, so that's when you're looking at the data booklet and you're seeing all of these pKa values. All right, this is actually the method that they would use in order to determine that. All right, so why do we call, what does this have to do with buffers? All right, when you look at, if you think about what's going on in this region from here to here, think about what we're doing. You can add a significant amount of acid or base. All right, so let's say that we added 1 milliliter. All right, how much does the pH change during that distance right there? Not very much. There's very little vertical rise when you're adding strong base in this direction. If we added strong acid to this and went back in the other direction, you notice it also doesn't change that much. So that's why in these acid-base curves, this region right here is considered the buffer region. All right, because you can add strong base and take it to the right, and the pH doesn't change that much, or you could strong acid and take it to the left, and the pH doesn't change it that much. One other aspect that this demonstrates is that even though ideally we want to have 50-50 of these guys, you can actually have slightly less off that. So notice if you had something that was right here, you could add either base and it wouldn't change that much, or acid and it wouldn't change that much.